Okay, so I've decided to try recording this lesson since we've had some problems with the internet previously. I'll have this as a way that'll work for sure. Okay, so we're talking about simple harmonic motion and conservation of energy and how we figure out how fast these objects are moving at any point during their oscillation. But first of all, let's talk about acceleration first. So, acceleration. These objects are obviously going to be accelerating at some points during their oscillations because their velocity is changing. So anytime we have a change in velocity, we have a acceleration is present. So let's talk about what is happening with a mass spring system first. So let's just draw a quick little diagram here. And we've got our mass. Let's say that this here is our equilibrium point. So we've got a mass that has been stretched out by some distance x. And at this point, I want to know how fast is it accelerating. How fast does it accelerate? Okay. And so turns out calculating the acceleration of these things at any one point is easier than calculating the velocity. So remember, at this point, since we've got it stretched out some distance, there is going to be a restoring force here, this force F, and remember this force F is going to be equal to k times x. And so this was the net force that is being exerted on this mass here. Remember when we're talking about net forces, remember that force net is equal to mass times acceleration. So really this here is a net force. This is the spring force. It's also the net force because we're only talking about the one force that's acting on this. So really what that's saying is that mass times acceleration is equal to k times x. So this is our spring constant multiplied by the distance that we've stretched it is equal to mass times acceleration. So if we want to figure out what the acceleration is, well, it's just going to be k times x divided by m. So this is a nice little way of calculating the mass of an object. One little thing I wanted to mention here. So as we've got our object, it's oscillating back and forth. And I'm not going to draw the spring this time. I'm just going to draw the two boxes. Let's say this is our equilibrium point. And the object is going to be stretched out some distance. And then it's going to oscillate back to the other side here. And also be stretched out some distance there. The maximum distance that it is stretched out, sometimes we call this the amplitude, but I don't always use that term. I just call it the distance x. So let's say we wanted to know what the acceleration is at a couple of different points. So when it is fully stretched out the most, well, what's happening here is that the acceleration is at a maximum here. And it's also fully stretched at this point over there. And the reason that acceleration is at a maximum is if we look at our little equation for calculating the acceleration, well, whenever x is the biggest, big X means big acceleration, right? So k and m are always going to stay the same. So our acceleration gets bigger the further that we stretch it out, assuming that it's oscillating back and forth. We don't have anything holding it in place. So hopefully that makes sense, is that when it is fully stretched out, that is when it is accelerating the most. So the further I pull it out, the bigger the force on it, the bigger the acceleration. And if we want to think about where the acceleration is at a minimum, well, looking at our equation, again, a equals kx over m. So this is telling us that when x is small, as x goes down, Well, obviously our acceleration goes down as well. And the point where x is the smallest is x goes all the way to 0 at one point. So when x equals 0, so this is basically when the amount that is stretched is equal to 0, well then our acceleration is also equal to 0. So this is when the object passes the equilibrium point. Is when the acceleration is actually 0 at that point, before it starts to accelerate back in the other direction as it moves across. So it's important to remember these 2 points here, is that the acceleration is at a maximum when it's fully stretched, and it's 0 when it's right at the equilibrium point. And it's actually very similar for pendulums as well. So for pendulums, we've got kind of the same situation here, where there's our equilibrium point. If we have our object is fully stretched, let's say, instead of fully stretched, I guess it's fully pulled off to the side, we've got some angle here. And for a pendulum, again, the maximum acceleration is when displacement is the biggest. When displacement is maximum. So remember, the reason for this again here is that our restoring force in this case, if you remember, we derived it, we said it was equal to the force of gravity times sine of theta. And so if we were to graph this, we could see that as sine of the angle goes up, then the restoring force also goes up. So as this angle gets bigger, the restoring force gets bigger, and so then the acceleration also gets bigger. This is going to be equal to, this restoring force is going to be equal to mass times acceleration again here. So if we are to simplify this down a little bit, the masses cancel out, and we can see that actually in this case the acceleration is going to be equal to g times sine of the angle. And just like with the spring, the minimum acceleration occurs when we are passing the equilibrium point. This is right at the equilibrium point. Because right at the equilibrium point, the angle is equal to 0. And so that means the acceleration is equal to g times sine of 0 is equal to, sine of 0 is 0, so this is actually equal to 0 here, at the equilibrium point. So it's the same thing for pendulums and for springs, is that as the oscillation passes through the equilibrium point, we are actually at a minimum acceleration. We're all the way down to 0 acceleration. And the reason that it keeps going is just because of momentum, basically. So in the next video, we're going to talk about how we calculate the velocity at various points along the path. So